This will be our first lecture on equilibrium. In the second lecture, we'll focus on Le Chatelier's principle. So in this first lecture, we're going to address the first two of these objectives, which is to define what chemical equilibrium means. And we're going to talk about why a system, when it's considered to be at equilibrium, is dynamic, meaning it's not at rest. And that means that the system hasn't stopped reacting. It just means that the reaction has reached what's called equilibrium. So you'll see what that means in just a minute. So what you've studied for most of the part of the year has been reactions which go to completion, which means they are irreversible. So if we were to have a graph of the reactants and products, the concentration or amount of them in our test tube as we do a reaction, it would look something like this graph down here. And the reason we know it would look like this is because we know that the concentration of the reactants, pictured in pink here, starts at whatever amount this is, depending on how much you put in there, but always the amount of products starts at 0. And as the products get made, we see that the graph, the line shows their concentration increases, but what are products made of? Well, they're made from the reactants, so naturally it makes sense that as the products increase, the reactants are decreasing, and so at the end we end up with 0 reactants and lots of products. We're going to focus on a different kind of reaction, which is ones that are reversible. And a reversible reaction will reach a state of dynamic equilibrium, which means that the rate of the forward and reverse reactions will become equal. And we'll write that definition down in just a minute. But what I want you to see is different is that instead of the reactants going down to 0 eventually, which is what we saw in the previous graph, we see that the reactions reach a steady state here, meaning their concentration becomes constant, and the concentration of products also becomes constant. And so equilibrium does not mean that the reactants and products equal each other, because these lines are not touching. It means that the rates are equal, and we see that in our graph in that if the rate of the reactants being used stays constant, and it's the rate of the products being made is constant, and there's recycling going on where the products are remaking the reactants, then we see that the amount of reactants and products stays constant over time. So let's write down these definitions here. Chemical equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. And again, rate just means speed. It's another word for saying speed. So the speed at which the forward reaction occurs is equal to the speed at which the reverse reaction occurs. And this is basically recycling. The forward reaction is the reaction described as the way you're used to reading them, where the reactants are on the left and they're making the products on the right. So we say the forward reaction is the reaction between the reactants to make the products, and the reverse reaction is the opposite. It's the reaction where the products are remaking the reactants. And as we saw in the graph, at equilibrium, the concentration of each substance, reactants and products, remains constant. It doesn't mean they're equal. The equal part in equilibrium, again, is the rate of the forward reaction and rate of the reverse reaction. So, for example, we know when we look at an equation, we know it's at equilibrium because we see this double arrow. But we need a way to describe the arrow on the top and the arrow on the bottom. So we've used the terms forward reaction and reverse reaction. So in this reaction where you have H2O and CO combining to make H2 and CO2, we would say the forward reaction describes the reaction where the H2O and CO are making the products. And we would symbolize that with the arrow pointing from left to right. So the arrow pointing from left to right, meaning from the left side, which is always, always, always the reactants, and the right side, which is always considered the products. So in the direction we read, we call that the forward reaction. When we're talking about the reaction going in the opposite direction, where the products are combining and getting recycled to make the reactants, we call that the reverse reaction because the arrow is pointing in the reverse direction. It's pointing backwards from which we read. Normally we read from left to right, that's forward. If it's pointing in the opposite direction, it's reverse. It means the same thing as backwards, but in chemistry we just tend to use the term reverse. So at equilibrium, we have forward and reverse happening at the same speed. So if we were to graph this reaction, it would again look like this graph we saw where they become parallel because this is a system which reaches equilibrium. So the amount of the reactants, which for example H2O is one of our reactants, we see it starts at some amount and product starts at 0. But over time, as H2O gets used up, H2 increases because as H2O is getting used up, those two H's make H2. But eventually we see that they reach a state of equilibrium at approximately time equals whatever this number is on the graph. And we know that's when they reach equilibrium because we see their concentrations become constant. It's not that the amount of H2O is equal to H2. Those are not equal. The concentrations are constant, symbolizing that the rate of the forward reaction at which H2O is used up is equal to the rate of the reverse reaction at which H2O is being made. So again, H2O is basically being recycled here. And if the recycling rate is equal to the rate at which it's used up, we reach the state of equilibrium. Let's look at an animation from this website down below from Glencoe Science. And we're going to look at, basically we're going to see a picture of what the molecules look like when we have a system that reaches equilibrium. So let's look at a different equilibrium system, and this is one that we had seen in the classroom where we had a tube of gas, and this was an equilibrium system between nitrogen dioxide and dinitrogen tetroxide. So let's look at, we see our similar graph if we start with NO2. And so NO2 looks like Mickey Mouse and the N2O4 is two of them stuck together. So we see over time that these NO2s are combining, and we see that their concentration is going down and N2O4 is going up. But now we see that they've reached a steady state, and if we watch the molecules, we see that every time one comes together, one gets broken up. These come together, these break up. So the rate of the forward reaction at which two of the Mickey Mouse NO2 molecules are combining to make N2O4 is equal to the rate or speed at which the N2O4 is breaking up to make NO2s. So we see that if the rates are equal, the overall total number of molecules in the NO2 conformation is going to be staying the same. And the overall number of molecules in the N2O4 stays the same. It doesn't mean that the NO2 and N2O4 stay equal to each other, but the rate, the amount of them stays constant. And we can see that in the graph here where they've actually measured the amount of them. And they said that at equilibrium, when we know this is equilibrium because the lines become parallel, showing that the concentrations become steady at whatever this amount is. Apparently it's 0.0898 molar and 0.0204 molar. They stay the same. So in our third lecture that we're going to have on equilibrium, we're going to use these numbers and we're going to calculate what's called the equilibrium constant, which is K. And it's basically a constant between, at equilibrium, how much of the reactants are there compared to how much of the products. So it's sort of a ratio or a fraction. So we'll come back to these numbers. So in the meantime, don't worry about these numbers. But again, what I want you to know is that equilibrium, for every time that the forward reaction is creating, in this case, the N2O4, we saw that an N2O4 broke up and recycled its material to make the reactants, which was two NO2s. In our next lecture, we're going to look at what happens if we have a system at equilibrium and we disturb it by changing the amount of one of these systems. And we're going to be able to predict what the system will do to go back to equilibrium.